let's finish this section by doing some last little thoughts and considerations about buffers. So we saw that they are used to prevent change in pH, making them extraordinarily important for biological systems. But we have a couple more things we can talk about with them. First off, we can determine how to make them. We can choose a pH of a buffer. So thankfully, we have many different weak acids, right? And we want to choose one that has a pKa around that of the pH that we're desiring. So you want to do that. If you want to have a buffer be at a certain pH, you want to choose one that's close to the pKa. So the pKa of our weak acid should be near the pH desired. So if you wanted a particularly basic pH, you'll want to use a very weak acid. So like something like ammonium and ammonia as your conjugate pair. Something where Kb is bigger than Ka, right? So if we hop over to Discord and we have our handy dandy list here, we have all these different pKa's, right? If we wanted a buffer with a pH around 5, we could choose anywhere from pyridine to propionic acid, acetic acid, hydrozoic acid, even benzoic acid there at 4.19 would work. We would be able to get a buffer with a pH of around 5. If we wanted one around 9, we could say choose hypobromous acid, hydrocyanic acid, boric acid, ammonium, or phenol. Any of those would work. And so we have a lot of options in choosing this. And once we do so, switching back to the tablet here, you can calculate the pH of choice by saying, I want a pH of 9, and I'm going to use, let's use, I want to use hypobromous acid. Why not? Hypobromous acid has a pKa of 7. That's hypobromous acid there. We can figure out what the concentration relative of these two would need to be in order to make that pH of 9. So we would have our concentration of hypobromite and of hypobromous acid. Generally, you can just choose one of these or it'll be given to you. So say I want the hypobromous acid part to be 0.25 molar. You can solve this equation by doing the anti-log here. You'd have 10 to the 0.3 would be equal to the concentration of the hypobromite, sorry. And this will be divided by 0.25. And you can solve for it this way. You have your hypobromite concentration would be, in this case, 10 to the, where's my 10 to the exponent? There it is. 10 to the 0.3. Oops. Okay, 10 to the 0.3 times 0.25. We will see that we want the hypobromite to be around 0.498, which, depending on the volume of your solution, that's molarity. You can then use volume to calculate moles, and then you can use your molar mass. Say if you want to use sodium hypobromite, you would be able to figure out how many grams you need to add to the solution to make that pH of 9. Notice that the base has a much higher concentration than the acid. The reason for that is because our desired pH is higher than that of the pKa. So we want more base around than the acid. So makes sense. Another thing is that buffers have a capacity. They have limits. Generally speaking, they will be able to buffer pretty much based on their concentration. So the more concentration you have, of each HA and A minus, the more you can kind of, the higher your capacity is. So the more strong acid or strong base you can add without the pH changing drastically. So it is dependent on the concentrations of your conjugates. Also, the buffers protect the pH in a range of plus or minus 1. So if we have that buffer of pH 9, we can generally add enough, we can stop the pH from changing drastically until it gets above 10 or below 8. At that point, it'll start changing very rapidly because we will have completely used up our buffer capacity. So buffers usually will keep your pH pretty evenly between one pH unit. And again, the more of the conjugates you have in there, the tighter that range is going to be. And just for some experimental, I have some numbers here. If we had a 0.3 acetate and acetic acid buffer, whoops. If we had a liter of this and we added 5 mils of 4 molar NaOH, the pH of this originally, since they're the same, would be 4.74. If we add this NaOH, small amount, we get a pH of 4.8. Not very much. However, if you just take 1 liter of water and add 5 mils of this NaOH, pH of this would be 12.3. So huge pH change, right? pH of the water should be 7 even, right, if it's pure water. So this is the power of buffers. You see the pH change for the second case is 5.3. That's 10 to the 5th power, plus some extra. So that's a huge change in concentration. Versus with the buffer, that's not a 9, that's a 4, by the way. We've changed it by 0.06. And that's not even a very concentrated buffer either. 0.3 molar, pretty low. So that's just illustrating the power of these things. So your buffer can be very, very useful. And you'll very often use them in biological reactions, or if you need the pH tightly controlled for a chemistry reaction. Buffers are a great way to do that. All right, so that's it for buffers. Next, we're going to talk about titrations. So how the pH changes as we mix acids and bases together. We can see that reaction happening and evaluate the pH at different points along the way. And so that's coming up next.